Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Atoms and Molecules. This is a lab manual in Unit 2. Section 1, Kinds of Matter. Lightning and glass. One bolt of lightning is 5 times hotter than the surface of the sun. It can reach temperatures of 29,727 degrees Celsius or 53,540 degrees Fahrenheit. If that bolt of lightning hits the sand in just the right way, it can turn the sand into glass. It does this because lightning carries a huge amount of energy. Remember that energy is the ability to do work. When lightning hits the sand, it transfers a lot of that energy to the sand. In rare cases, this energy can cause some of the grains of sand to change into glass. To change means to make something different from what it is now. Think about the properties of sand and the properties of glass. A property is an observable or measurable characteristic of a substance. For example, both sand and glass are solid, but sand is coarse and opaque. Opaque substances don't let light through. In contrast, glass is smooth and transparent. This is why glass is used for windows, glasses, and other functions where you need to see through it. Function is the normal action of something or how something works. When lightning strikes sand, it sometimes forms a glassy tube. This tube is often in the shape of a miniature lightning bolt. This kind of glass is very fragile and will break apart easily. Introduction to matter. Understanding how lightning can change sand into glass begins with an understanding of matter, anything that has mass and takes up space. Remember that mass is a physical property of matter. It is a measure of the amount of atoms, or matter, that make up an object or substance, and it is measured in grams. Physical properties are features of a substance that can be observed or measured without changing the chemical structure of the substance. In addition to mass, physical properties include color, odor, density, volume, shape, boiling point, and melting point. Chemical properties are features of a substance revealed during a chemical reaction. Chemical properties include flammability, the ability to catch on fire, oxidation, the ability to react with oxygen, and reactivity, the ability of 2 or more substances to combine together. Atoms and elements. Both sand and glass are kinds of matter because they are both made up of atoms. An atom is the smallest piece of matter that has the properties of an element, substances that are made up entirely of one kind of atom. The air around you is matter, as are all living things and all of the stuff that surrounds you. Energy is not matter because it isn't made up of atoms. However, energy and matter are constantly interacting. Matter can only change when enough energy is present. We'll explore these ideas in the next sections. To understand why a substance has the properties it does, scientists begin with the structure of the atoms that make it up. Structure is the way in which parts are put together to form a whole. Scale of an atom. Atoms are so tiny that we cannot see them without special instruments. Just 1 grain of sand is made up of many millions of atoms. Because of this, scientists use scale to better understand the size of an atom, including how the parts that make it up relate to one another and how the size of an atom relates to everyday substances. Scale is the size, extent, or importance, magnitude, of something relative to something else. For example, think about a grapefruit. If each atom in the grapefruit were the size of a blueberry, the grapefruit would have to be the size of Earth. There are so many atoms in just one grapefruit that they are impossible to count. Imagine having to fill up the entire planet with blueberries. That's about how many atoms are in one grapefruit. Parts of an atom. Atoms themselves are made up of smaller particles called protons, neutrons, and electrons. These smaller particles are called subatomic particles. These smaller particles are much smaller than the atom itself. For example, the protons and neutrons group together in the atom's core, called the nucleus. If the atom is the size of a blueberry and you open the blueberry up, the nucleus would be too small to see. If you were to make the blueberry the size of a football field, you would just be able to see the nucleus. It would be the size of a small marble. The nucleus holds all of the atom's protons and neutrons. The electrons are much smaller than the protons and neutrons. They are in constant motion around the nucleus. However, most of the atom is filled with empty space. There are vast regions of space between each of the electrons and between the electrons and the nucleus. Understanding density. The nucleus of an atom is very dense. Density is a measure of the amount of mass in a given volume. Volume is the measure of how much space a substance takes up. The more tightly packed the molecules of an object are, the denser they are. This is because they have more mass in a given volume than materials that are less dense. The nucleus is very dense because 99.9% of the atom's mass comes from the protons and neutrons. Density is a physical property of matter. This is because every kind of matter is made up of atoms. Density explains why two objects of the same size can differ in mass. The density of any object is calculated by dividing the object's mass by its volume. This is the equation: density equals mass divided by volume. Density is a useful physical property for identifying an unknown substance because the amount or sample size of a material does not affect its density. Because most substances change volume when they are heated or cooled, densities are temperature dependent. Atomic structure. Scientists use what they know about an atom structure to create a scale model of an atom. Scale models are useful for scientists who want to understand the atom as a system and how the various parts of the atom interact. For example, scientists believe that a single atom looks something like a mini solar system. Protons have a positive charge and attract negatively charged electrons. Protons also pair with neutrons. Neutrons have a neutral charge and pair with positively charged protons. Protons and neutrons pair together in the atom's nucleus. Electrons have a negative charge and are attracted to positively charged protons. Electrons travel around the nucleus like planets orbiting the sun. They move because they are attracted to protons in the nucleus. Orbiting electrons. Electrons orbit at different distances called shells. Electrons like to stay close to the nucleus. However, each shell can only hold a certain number of electrons. The innermost shell holds 2 electrons, and the second shell holds 8 electrons. The third shell holds 18 electrons, the fourth shell holds 32 electrons, and the fifth shell holds 50 electrons. The farther a shell is from the nucleus, the more electrons it can hold. For example, neon is a small atom that has 2 shells with 10 electrons. Radon is a large atom that has 6 shells with 86 electrons. Periodic table of elements. Scientists rarely work with individual atoms because they are so small. Instead, they work with elements such as a gold bar or helium gas. An element is a pure substance because it is made entirely of one kind of atom that has distinct properties that do not vary from sample to sample. Many of an element's properties are determined by the number of protons and neutrons its atoms have. Other properties are determined by an atom's number and arrangement of electrons. In the picture above, each gold bar is made up of many billions of gold atoms. It is the structure of the gold atom that gives the gold bars the properties that they have. For example, gold is a soft, yellow metal. It is also malleable. This means it can easily be bent or shaped. It is also ductile. This means it can be hammered into thin sheets. All of the known elements are organized according to their properties in a chart called the periodic table of elements. There are currently 118 known elements. The last 4 were just added in 2016. These 118 elements are the only substances needed to make all of the materials that exist. In the human body, there are many billions of atoms, but scientists believe that more than 95% of the body is made up of just 6 elements: hydrogen, carbon, nitrogen, oxygen, phosphorus, and calcium. Each element on the periodic table is assigned a symbol and a number. The symbol comes from the name of the element's atom, in English or Latin, and the atomic number comes from the number of protons found in the atom's nucleus. Neutrons and electrons don't define an element because the number of neutrons and electrons in an atom can fluctuate. The periodic table is organized from top to bottom in groups by increasing atomic number. The periodic table indicates some patterns among elements. For example, an element's place on the periodic table tells us about some of its properties, including how reactive its atoms are and whether it is a metal, nonmetal, or metalloid. Metals are shiny, malleable, and good conductors of electricity and heat. Almost 75% of all elements are metals, including gold and iron, and other elements in columns 1 through 12 of the periodic table. Nonmetals are brittle, dull, and poor conductors of electricity and heat. There are only 17 nonmetals on the periodic table. Gases and elements on the far right of the periodic table are nonmetals. Coal is an example of a nonmetal, as is oxygen. Metalloids are found between metals and nonmetals on the periodic table. They are also called semiconductors because depending on what other molecules are around, they can sometimes conduct electricity. Metalloids have properties of both metals and nonmetals, such as being shiny and hard but brittle. Boron, silicon, and arsenic are metalloids. So here is the periodic table of elements. Section 2, Forming Matter. Libyan desert glass. In 1996, an Italian scientist noticed an unusual gem in one of Tutankhamun's necklaces. Tutankhamun was an Egyptian pharaoh who ruled between 1331 and 1323 BC. He is sometimes called King Tut. The Italian scientist was interested in a yellow-green gem that he saw in King Tut's necklace. When the gem was tested, it was found to be glass. However, it was older than the oldest Egyptian civilization. What formed the glass? How this glass was made is a question that scientists are still trying to answer. It came from a stretch of desert in Africa called the Libyan Desert. More than 1,000 tons of this kind of glass have been found there. Scientists have dated this glass to be more than 26 million years old. It is generally yellow, and it can be translucent or almost opaque. Translucent substances can partly be seen through. Opaque substances block all light. Scientists believe that this Libyan desert glass may have formed when a meteorite hit Earth or when a comet from space exploded in Earth's atmosphere. Both of these events would have provided the extreme temperatures necessary to change the desert sand into glass. Glass's state of matter. Glass is unlike any material on Earth. Scientists sometimes refer to glass as a rigid liquid because it isn't quite a solid and it's not exactly a liquid. This is because of the extreme temperatures that form glass. Whether a substance is a solid, liquid, or gas depends on the amount of thermal energy present. All matter has thermal energy, which is the motion of atoms and molecules in a substance or object as its temperature increases. Temperature is a measure of heat. Heat is energy transferred when two objects or systems are at different temperatures. It always transfers from hotter substances to cooler substances. The faster that atoms and molecules move, the more thermal energy they have and the warmer they become. Sand is a solid at room temperature. The atoms in a solid are closely packed together. They are always moving, but because of how close they are, they can only vibrate in place. They cannot move past one another. Because of this, solids keep their shape until something changes them. When thermal energy is added to solids, the atoms or molecules begin to move more quickly. When enough energy is added, they will expand and become a liquid. The temperature at which a substance changes from a solid to a liquid is a property of matter called its melting point. This is what happens when lightning or a meteor comes into contact with sand. When sand is heated to such a high temperature that it melts, it becomes a liquid. Its atoms and molecules are moving much faster and can slide past one another. Different substances have different melting points, depending on how much energy is needed to change them from a solid to a liquid. This, in turn, depends on the kind of atoms that make them up. The atoms in a liquid are less tightly packed than in a solid. They are in constant contact with one another, but they have enough energy to slide past one another. Therefore, matter in a liquid state takes the shape of its container, but has no shape of its own. When thermal energy is removed from a liquid, the kinetic energy from the atoms and molecules decreases. This causes them to slow down. When enough thermal energy is removed, the liquid will turn into a solid. This is called its freezing point. For example, water freezes when the temperature reaches 0 degrees Celsius or 32 degrees Fahrenheit. The freezing point of a liquid substance is generally the same as the melting point of a solid of the same substance. Glass is so unusual because it is formed when liquid sands cool so rapidly that there isn't time for the regular, repeated pattern of sand's molecules to reform. Because glass has cooled, however, its atoms and molecules are held rigidly in place so they cannot flow. This is why glass is sometimes called a rigid liquid. Glass blowers use this scientific knowledge about the molecular structure of glass to produce many different kinds of products. For example, there are many different kinds of glass made today with unique chemical and physical properties. When enough thermal energy is added to a liquid, the atoms or molecules will move so quickly that the liquid will expand, becoming a gas. This is called a substance's boiling point. The molecules in a gas have so much energy that they move far apart and bounce around randomly. As a result, matter in a gas state has no shape and spreads out into space. If a certain amount of gas is taken out of one container and placed into a container that is twice as large, the gas will expand to fill the larger container. Molecules and compounds. Libyan desert glass has different properties from glass formed by lightning. However, both come from the same elements. Most glass is mostly made up of the elements silicon and oxygen because these are the main elements of sand. Atoms are like Lego pieces. They can fit together with other atoms to form bigger pieces of matter. Atoms combine by forming bonds with other atoms. To bond means to join together. Whenever two or more atoms bond, they form a molecule. A compound is a combination of two or more different kinds of atoms bonded together. Molecule or compound. Oxygen is a molecule, but not a compound, because it is made up of two oxygen atoms bonded together. In contrast, water is both a molecule and a compound. It is made up of two hydrogen atoms and one oxygen atom. Like gold, water is also an example of a pure substance. It is made up entirely of one kind of atom or molecule that has distinct properties that do not vary from sample to sample. Sand is primarily made up of the compound silicon dioxide. Silicon dioxide is also called silica. Each molecule of silica contains one atom of silicon and two atoms of oxygen bonded together. One of the reasons that Libyan desert glass is so unusual is that it is the purest natural silica glass ever found on Earth. Most sand contains a mixture of different molecules in addition to silica. Molecules and compounds are formed in chemical reactions between two or more atoms. In a chemical reaction, the atoms that make up the original substances are rearranged into new substances that have different properties from the original substances. For example, at normal room temperature, both oxygen and hydrogen elements are gases. When hydrogen and oxygen bond in a molecule of water, they change into a liquid instead of a gas at room temperature. These changes are chemical changes because they rearrange the chemical structure of the substances through a chemical reaction. Chemical changes are different from physical changes. In a physical change, the chemical structure of a substance is not affected. For example, if you cut up a piece of paper, it has changed, but it is still paper. In any chemical reaction, the atoms and molecules that interact together are called reactants. The atoms and molecules produced by the reaction are called products. When the reactants come together, energy breaks the bonds holding the reactants together and rearranges them to form new products. Molecules and compounds hold a form of potential energy stored in their bonds. This potential energy is called chemical energy. Remember that matter can only change when enough energy is present. The total number of atoms does not change in a chemical reaction. Because of this, the mass of any one element at the beginning of a reaction will equal the mass of that element at the end of the reaction. This is called conservation of mass because matter is never created or destroyed. This means that the more reactants you add to the chemical reaction, the more products will form. It is always true that mass is conserved in a chemical reaction. However, this can be difficult to measure in the real world because matter can interact with the environment. Remember that if a gas is produced, it will fill whatever space it is in. This is impossible to measure in an open system. For this reason, scientists sometimes conduct closed system experiments. These experiments are designed so that matter cannot be exchanged with the environment. This allows scientists to measure the effects of the reaction. Chemical bonds. Molecules and compounds bond because of the attraction of protons and electrons. When two atoms approach one another, the electrons of each are attracted to the protons of the other. Atoms bond because they seek full atomic shells. Some atoms have just a few electrons in their outer shell. These atoms are likely to transfer those extra electrons to atoms with nearly complete outer shells. Sharing electrons. Sometimes two atoms do not transfer electrons between them. Instead, they share the electrons. Water is an example of a compound created by shared electrons. The oxygen atom needs two more electrons to have a complete outer shell. The hydrogen atoms each need one electron. When the hydrogen and oxygen atoms bond, the oxygen atom shares one electron with each of the hydrogen atoms, and the hydrogen atoms each share one electron with the oxygen atom. The water molecule is joined by a double bond. A double bond is formed when two or more atoms share 4 electrons. Some molecules are joined by a single bond, when 2 electrons are shared. And other molecules are joined by a triple bond. This is formed when 2 or more atoms share 6 electrons. Section 3. Energy changes matter. A professional glassblower. Kiva Ford spends his days making complex glass instruments that scientists use in the laboratory. When he comes home from work, he focuses on artistic glass structures. He designs goblets, flower vases, and intricate animal sculptures. For professionals like Kiva, glass blowing combines art and science. To create scientific instruments and elegant glassware, glassblowers need to have a deep understanding of what glass is, how it is formed, and its molecular structure. Kiva's interest was sparked in part by one property in particular, glass's state of matter. My experience with glass was that it's solid, Kiva said in an interview with the e-commerce website Etsy. And then when I was introduced to glassblowing, all of a sudden, it's not a solid anymore. It's a liquid. It almost feels like honey in between your hands. Energy transfer, exothermic processes. Glassblowers all work with torches. A torch is a tool that produces controlled fire at the end of it. The torch produces the extreme temperatures needed to shape and form the particular shapes needed in glass blowing. Torches work because of a chemical reaction. In any chemical reaction, the reactants and products form a system. The environment is everything else, including the air or any substance mixed with the reactants. As the reactants combine and rearrange, energy is exchanged between the system and the environment. Every chemical reaction needs energy to get started. This initial input of energy is called activation energy. For example, when someone strikes a match to light a candle, they provide the activation energy needed to start a fire, which is a chemical reaction. Once the reaction begins, some reactions absorb more energy from the environment than they release. Others release more energy into the environment than they absorb. Any process in which the system loses heat to the environment is called exothermic. Exo means to give off. Because the energy is released as heat, the environment's temperature will increase. The environment's temperature increases because it means that the reaction has released thermal energy into the environment. Endothermic processes. Whenever a process occurs in which the system absorbs heat, it is called endothermic. Endo means to draw in. In an endothermic reaction, the environment's temperature decreases. This is because the reaction has absorbed energy from the environment. A chemical ice pack uses an endothermic reaction to get cold. Many ice packs have ammonium nitrate and water kept in separate sections within a thin barrier between them. When you break the barrier, the water and ammonium nitrate combine. They absorb energy from the environment. This is why the ice packs get cold. When the reactants have fully reacted, the chemical reaction stops. The strength of a chemical reaction can be measured by the amount of energy absorbed or released by the reaction. When more reactants are combined in a chemical reaction, the amount of energy that is absorbed or released increases. Wow, I learned a lot reading Atoms and Molecules. I hope that you did too. I'll see you tomorrow with another one. Bye.